I will give you a brief introduction to planet Mercury, especially for concerning its surface stratigraphy, tectonics, and geology in general. So let's start looking at Mercury from far. And in here, one of the two bodies is Mercury. And I know you have studied hard, so you may have recognized the moon on the left side. And on the right side, we have Mercury. You can see how the two bodies are very, very similar. They are both full of craters. They have very similar bond albedo values, especially if we look at the moon from the far side. And they are so similar because they both were bombarded by craters. They have many craters on their surfaces. They don't have an atmosphere that could allow for too much changes on the surface, but the main difference, the first main difference we notice is that Mercury is just densely cratered, not as heavily cratered as the moon, because with the first main difference between the two bodies is that what we observe on the highlands of the moon is the original magma ocean, the original crust. It's the primary crust that was bombarded since the early formation of the moon. While on Mercury, we had several events of resurfacing of the surface via volcanic floods and lava floods. So that's why if you count the craters, and someone actually did this, you will notice that on Mercury we have less craters than on the moon. And as on the moon, we have also fresh craters with bright rays, and probably Mercury has even more bright rays than the moon has. Let's have a look at Mercury from the albedo maps. These are albedo maps. So the contrasts, gray contrasts are very exaggerated here, and they reflect the compositional differences. And you can see on the on the hemisphere of Mercury center at the prime meridian, you have this very bright fresh crater, which is the Kuiper crater. This crater and its rays define the youngest period of Mercury, which is called the Kuiperian period. On the other side of the planet, at the center at the anti-meridian, you have this very dark and subdued crater here, which is called the Tolstoy crater. And this crater instead defines the stratigraphy for the oldest period of Mercury, the Tolstoyan, and before that, the pre-Tolstoyan. If we look at the topography of Mercury, we can see that it's pretty dominated by craters, also in its topography, but the highest point is found in the meridian side, and it's plus 4.5 kilometers. And the lowest point is still in the meridian side, with the lowest point being minus 5 kilometers within the Rachmaninoff basin here. On the northern part of Mercury, the North Pole and the northern high latitudes, you can see there is a pretty low terrain, very smooth, something similar to what we observe on Mars, okay? But it's not so strong. The dichotomy is not so strong here, but still we have this planitia, which is called the Borealis planitia, and it is a very wide lava plains we have, and the youngest lava plains we have on Mercury to the north. If we look at the instead at the enhanced color mosaic, these are false colors. These are not actual colors of Mercury, but these enhanced color maps help us understanding the compositional differences of the planet. You can clearly see that in here we have another important planitia. This is very large. It's 1,500 kilometers wide, and it's called the Caloris planitia. It's actually the largest basin of its age in the solar system. So this is a very important basin on Mercury, and as you can notice, the topography around it is resurfaced because of its impact with respect to the plains that are very far from the basin. And then we have this dark blue material, which is called the low reflectance material, which is thought to be the original, a remnant of the original crust, maybe graphite. So we have seen how the global stratigraphy is overall defined. So let's have a look to Mercury in comparison to the Earth. We can see from this scheme where you have the several eons and ages of Mercury, you can see that what we know about the planet is complementary to that, to what we know about the Earth. On the Earth, we know much about the present day. Maybe yesterday you did Venus, if I recall well from your program. So you may have studied that Venus, we only know these. We have evidence only for this short period of 500 million years, while for Mercury, we know a lot about the early formation of the planet. So we're talking about the Tolstoyan, the Calorian, which is the period defined by the Caloris basin, and we know a little about the Manchurian and the Kuiperian periods that are the earlier periods of Mercury. So this red area represents the late heavy bombardment evolution. So what we look at when we look at the surface of Mercury, we see much of what happened in the early period of the late heavy bombardment. And why it is important to study Mercury? Because it provides a window to the early formation of the planets of the solar system. So again, here you can see the surface of Mercury in its enhanced color, and this enhances the geological diversity of the planet. And as I said before, it's entirely covered by volcanic units, meaning that its crust is a secondary crust. It's not a primary crust as that of the moon. There are still some studies ongoing on the blue parts where we may have some primary crust resurfaced and left at the shell, in the shallow surface, but mainly what we see on Mercury, it's secondary crust. It's several layers of volcanic events that stratified one over the other during the early formation of the planet. So this is, I already said this, so we have a secondary crust that was created by the flooding of lavas that raised from the fracturing and by the fracturing that the craters created on the surface, more or less what you can see on the lunar maria today. But these happen on the whole surface of Mercury. And As you can see from this picture, craters often tells us more about the stratigraphy of the planet. For example, in here, we are in the yellow plains of the Caloris planitia, and these craters exhume at their rim some blue material, telling us that below these yellow plains, we have the blue and older material. And we also have these cool features here that I will talk about later on. So to understand the geological units that are on Mercury, we can start from the definition of Trask and Guest that was given in 1975 in the Mariner 10 era. So on Mercury's surface, morphology reflects the age, composition, lithology, and mode of formation of the underlying rock unit. And this is more or less true if we look at the at the surface from the pure morphological point of view. Indeed, the smooth plains are the youngest unit on Mercury. The intercrater plains are the oldest unit on Mercury. And then we have some intermediate plains that are smoother with respect to the intercrater plains, but they are more tectonized, deformed, and cratered than the smooth plains are. If we look at the colors instead, we don't have a precise correspondence between the morphological units and the color units, where we can say that most of the times the intercrater plains look blue, but it's not rare that we can find also red intercrater plains. Intermediate plains can have an intermediate colors, but we can also find blue intermediate plains. Most of the smooth plains often have a yellow color, but we also have smooth plains with a brownish color. So it's important that when we talk about the geology of Mercury, we start from the morphology, but then we slowly move to the interpretation and integration of the colors to understand better the lithostratigraphic units that actually exist on Mercury. So our group usually builds geological maps to understand the surface. And so we map these geological units that you have just seen, and then we classify craters just to have an idea of the order of the events. So we use these maps as a book to read the history of Mercury. And if you need geological maps for this planet, they are available on the Mercury Quick Map website. And the ones that were published so far are the one in green here, and the other are being completed. So these maps are available online, or you can if you need some geology from the regional scale, you can email me and I can provide you the shapefiles. How did we build our geological maps? I already said how we distinguish the three main geomorphological units. And then we classify craters either in 3 degradation classes or 5 degradation classes. The 5 degradation classes were published by Kinjik et al. 2020, and they aim at finding a correspondence between the morphology of the crater and the age of the crater. And this is often applicable to craters that are larger than 40 kilometers. In our geological maps, we often we map also craters that are larger than 20 kilometers. So we often we prefer this 3-class system that allows us for a more simple and direct classification of these craters. And indeed, if we plot crater densities after mapping a quadrangle, you can see that there is an actual correspondence between the morphology of the mapped unit and their actual age derived from counting craters. So here with the brown, we see the intercrater plains that actually have more craters and larger craters. And then we have the intermediate plains here and smooth plains here, which are clear, definite, and the youngest unit. And so the three crater classes sometimes will allow us for distinguishing these units, as only C3 craters are found on top of all of the youngest smooth plains on the planet. And in here, the example is of the smooth plains from the northern Borealis planitia. Then what we see on Mercury is that the surface is intensely tectonized and deformed by wrinkles and scarps. So we can find wrinkle ridges on the smooth plains and long lobate scarps on the intercrater plains. Wrinkle ridges are found also on the lunar maria, but we don't have as many wrinkle ridges as on Mercury. So on Mercury, we have thousands of scarps, and scientists have tried over time to reconstruct the tectonic history of Mercury. Let's say that the three main proposed models are still the global contraction, tidal despinning, and mantle convection. The global contraction being the most, let's say, the model that most scientists still follow today. So the core of Mercury is shrinking while it solidifies, and so it should create random scarps around the planet. But since many observe some alignments of scarps around the planet, during the Mariner 10 era, they started to think about the tidal despinning model that foresee a rotation despinning of the planet, an inversion of the tectonics, where we had the equatorial bulge of the planet. So we had the equatorial bulge of the planet because the planet was rotating very fast. Then it suddenly had the spinning and a tidal break because some event that happened on Mercury, and this caused the inversion of the tectonics at the equatorial region. So we should have mainly north-south systems of faults and strike-slip faults at the mid-latitudes. And this model also predict east-west normal faults at the poles. Actually, we don't see a precise pattern as this one, but as we will see later, we can see some alignments that do not reflect the total randomness foreseen by the global contraction. Then someone also predicted mantle convection for the planet. The problem is that the mantle of Mercury is not as big as that of the Earth. I mean, with respect to the core, the mantle is very thin, so it soon became solid, and it soon started to became in a, let's say, in a conductive state instead of a convectional state. So if mantle convection ever existed, it should have existed for a short period of time. So here we see that Mercury have a very, very large core, and that's why, maybe the reason why we can see so many scarps at its surface, because if you shrink a planet because of the core that is solidifying, so it's the effect on the surface, since the outer shell is so thin, the effect on the surface should be very strong, and that's why probably we see on Mercury so many scarps. Okay, so here you see the comparison of Mercury with the with respect to the Earth, where you have a liquid outer core, but the entire size of the core is very huge. It occupies almost 50% of the volume of the planet, and the mantle, as you can see here, is very thin with respect to the mantle of the Earth. So the convectional state couldn't resist for long, and then any changes that happens in the core reflects well on the surface because the strength is so because it's the effect of the core is so strong on the outer shells. And so what are these scarps? These scarps are the surface expression of reverse folds, and especially they are low angle thrusts. So we have low base scarps that have an asymmetrical profile with a very low angle, let's say, reverse folds. Then we have high relief ridges that have a more symmetrical profile, where we probably have a main thrust and a back thrust in the lower part. And then the wrinkle ridges are also thought to be the expression of subsurface thrusts that cause, let's say, the folding of the surface on top of the thrusts. So this is the map from Byrne et al. 2014. We have some updates of the mapped folds around the planet. For example, we have also Mann et al. 2023, which is maybe the most updated version of the folds that we have on the planet. But in any case, statistically, we have thousands of scarps, and you can see from here, there is no clear alignment as in the tidal despinning example, but yet we have some very long alignments on the planet. And so in Byrne et al., they estimate a 5 to 7 kilometers radius change of the planet because of the shrinking, just by measuring the scarp length and relating it to the possible displacement that the scarp may have recorded. What is the age of the scarps? So let's say, when did this global contraction happen on the planet? Giacomini et al. Mapped and dated several scarp systems whenever they have the same consistent direction. And the outcome is that mainly scarps are 3.7 gigayears old. And this is the same results that I got in 2019 within the Victoria Quadrangle, where I have two different systems. And again, I get 3.7 gigayears. So these scarps are very old. They are in the late Tolstoyan. They developed mainly in the late Tolstoyan. So it means that when these volcanic plains formed, soon after they were also deformed by global contraction. But global contraction may be still happening today, but the effects are so small that we can only suppose that there is some global contraction by looking at some very, very small scarps that still form today. Curiously, this is a theory that was done for the Earth long time ago in 1829, when tectonics were not yet discovered. And so people were wondering how the mountains of the Earth were formed. And one theory was that the Earth was in a contractional state. And they thought they proved this by using some balloons in the laboratory, let's say. They did a contraction experiment on flexible balloons, seeing that these inflatable balloons that wrinkled after deflating. So they thought that the mountains on the Earth were due to the global contraction. Actually, it is important to say that global contraction doesn't create the stresses that plate tectonics creates on Earth. So global contraction alone cannot create the mountain ranges and that we have on the Earth. Still, it creates pretty long escarpments. So in the end, what we think today is actually global contraction acted together with tidal despinning at a certain point, and that should explain why we have many alignments across the planet. We think we see a pattern, especially in the equatorial and mid-latitude regions where we have north-south alignments. So probably the reason is that global contraction and tidal despinning acted together in the early formation of Mercury. But besides global contraction, we also see that many fault segments show a strike-slip component of displacement, and also faults show lateral ramps with strike-slip kinematics for large-scale systems. And with large-scale system, I'm talking about 100 kilometers of fault systems that show strike-slip kinematics at the lateral ramps. And this is compatible also with the existence of convective cells at the time of the scarp formation. So as you can see from here, the tectonic history of Mercury is very complex, even if the evidence at the surface is limited. It was characterized by many different stages of tectonics. So just to tell you that it's not just the global patterns of global tectonic models, but also the geochemical terrains may, let's say, may induce stress fields in some regions of Mercury. This area here is called the high magnesium region, and it occupies an entire hemisphere of Mercury. It's very, very huge, and it is so thought to have a very high densities and higher crustal thicknesses. And as you can see from here, the structures well align along its boundary. So it seems like that also the crustal dishomogeneous geochemistry in some way played a role in driving the stresses and the structures on Mercury. See, this is another example of the same region where we can compare the structure alignment with several chemical data, and especially with the crustal thickness and magnesium abundances, we can see clear alignments. The crustal thickness, these are not updated data. We have more updated data about crustal thickness, but still in this area, there is a huge alignment of the faults with the crustal thicknesses. After all, if you compare the length of the system, which is 1,500 kilometers to the Earth, so if you stretch Mercury to the size of the Earth, this would be as large as part of a border of a continent. It's like the boundary of a continent. So I'm not saying that we have plate tectonics on Mercury, but actually these faults played an important role on the asset of the crust. Finally, after the main tectonic events and the main volcanic events, we have also another kind of volcanism, which is the explosive volcanism. And so scattered around the surface of Mercury, you can find these faculae, which are called faculae by IAU. And you can well see them in an enhanced color-based map, that they are pretty bright, they are yellow, and they are pyroclastic deposits. And at the center of this faculae, you can see that you always have a vent, a volcanic vent. And you can see also in these vents several stages of disruption and venting. So as you can see also from here, for example, the Agua Facula, you have a part which is very subdued and a part which is more fresh, is fresher. So it means that this vent erupted several times in the history of Mercury. So explosive volcanism on Mercury is long-lived in the history of Mercury. And also, if we see that the relationship that these vents have with the faults, we can see that the vents often align with fault system. Again, we are in the longest fault system of Mercury, the Victoria system, which, as I said before, is 1,500 kilometers from here to here. And you can see here that you can find 1, 2, 3 explosive vents aligned along the fault systems. And even when these vents are not found along the faults, here is the discovery rupes, they are found right in front of the faults. So it seems there is a very strong relationship between explosive volcanism and tectonism. This is one work from our group that I'd like to show you, just to say that faults not only follow geochemical terrains, not only follow global patterns of tectonic models, they in particular follow the discontinuities created by ancient impacts. For example, here we have an ancient impact which is called the Andal-Coleridge Basin, which is very subdued. We cannot see the rim, we cannot see the floor, we cannot see the ejecta, but we can see that the faults align concentrically all around the ancient center of this basin. And in here, the global contraction exploited the ancient rings of this basin to use them as contractional planes. So we have also an inversion of tectonics from the extensional rings of a basin. They were contracted and used as planes for the thrust faults that created the scarps around this basin. So basins, ancient basins, play an important role in alignment of the faults around the planet. And also, we are talking about the surface today, but let's go a little into the subsurface, in the shallow subsurface. So if we look at the isostatic gravity anomalies, we can see there is also, in this case, nice alignments between the fault systems and the gravity anomalies, and especially the boundary analysis that is analyzed in these days by Salvatore Bonifante from our group, that can help us assessing the nature of tectonics on Mercury. Mercury is often ignored in the tectonic cycle of the planets, because, as you know, Venus, Mars show very outstanding examples of tectonics, and Mercury is often compared to the moon. That's where nothing happened. It was frozen at its early stages and stopped. But actually, what we saw today is that Mercury probably deserves something like an intermediate stage between a planet that has no tectonics at all and a planet that starts triggering the first planes for setting up some tectonics. Of course, I'm not, again, talking about plate tectonics. I'm talking about stagnant lead tectonics with a unique plate around the planet. And let's go on with the history of Mercury. So we talked about the effusive volcanism, tectonics, explosive volcanism, and let's go to another feature of Mercury, which is represented by the presence of volatiles around the planet. And to speak about this, we have to say that Mercury has a very high temperature contrast around its surface, because it's so close to the sun. When it faces the sun, it can reach up to 400 degrees. But when Mercury is at perihelion, since the perihelion is much closer than the aphelion, we can reach also up to 450 degrees. And these are called the hot poles, because Mercury is tidally locked to the sun in a spin-orbit resonance 3-2. So it means that when it's perihelion, it always faces either the prime meridian or the anti-meridian at the sun. And when it's at aphelion, it always faces either +90 or -90 longitude. So these are called the hot poles, and let's say the warm poles, and cold poles, actually. Actually, the cold poles are at the north and the south of the planet, but in the equatorial region, we can speak about hot poles and warm poles. Where we have the hot poles is where we have the highest temperature. And then, since the Mercury axis is pretty vertical, perfect, I would say perfectly vertical, it never faces the sun precisely at the poles. So it's always dark and also cold. So at the poles, North Pole and South Pole, they are called the cold poles, because we reach temperatures of minus 180 degrees for the whole solar day. And in the cold poles, they found evidence for the possible presence of water ice in the permanent shadow regions of the craters. While in what happens in the hot poles and warm poles, we have another phenomenon that that exploits volatiles in the surface of Mercury, and they are called hollows. Let's see what are hollows. So hollows are a very important feature of Mercury. They were discovered during the MESSENGER missions, so in the early, let's say, 2011. And they are often found within craters. If craters are very large and complex, they are often found around pink rings or central peaks, and they are very small cavities, flat floor cavities with irregular boundaries, and they seem to cluster together. These are the location of hollows across Mercury, and you can see that there is a good correlation with the hot poles and warm poles, where you cannot find any hollows in the cold poles. So how they form? They should probably form by sublimation of the crust of Mercury when exposed to the intense radiation of the sun. But there seems to be a correlation, not as precise as not so precise, but there seems to be a correlation with the low reflectance materials. So there is probably an interplay between the radiation of the sun and the composition of the surface. Latest results about hollow studies say that analyze their occurrence across the planet. And so since we find them, especially within craters, one may inquiry on whether the origin of the volatiles creating hollows is exogenic. But actually, thanks to the work of Barbara of this year, we can rule out the exogenic origin of a volatile material because hollows are found both in young and old craters. So also very old craters host fresh hollows. So they had all the time to lose the volatile materials they brought to the surface, but actually hollows still form today in these old craters. Then hollows are found also in large craters that were created from energetic impacts, so where the volatile bearing projectiles are unlikely to survive. So it is very likely that hollows are linked to an endogenic volatile layer, but this layer is at varying depths, because from this work we can see that there is not a constant depth where the craters formed and where the hollows formed within craters. And let's say that we in this work, Barbara also found that the activity of hollows is short-lived because they are so shallow features, so shallow features that they probably formed even in the past, but we have no trace of past hollows forming on the planet. So we only can see what was formed in the latest period of Mercury. So hollows are an outstanding question still existing today, and Bepi Colombo, the next mission to Mercury, will probably tell us more about their formation. One last but not least, it is important to say that all these things can coexist together. So hollows, volcanism, and tectonics coexist together, especially in some basins. And if we do a geological inspection of this basin where these things coexist together, they can be used as laboratories to understand the evolution of Mercury. This basin is the Praxiteles basin, and the Praxiteles basin is pretty old. It's maybe Calorian in age, but we can see that its floor was later resurfaced by volcanic infilling. And then after the volcanic infilling, we have that partially covered even the peak ring. After the volcanic infilling, we have the explosion of the faculae. These are the volcanic vents, and this red unit is the pyroclastic deposits that cover the infilling of the basin. And then we have the formation of hollows that overlies the pyroclastic deposits. So hollows formed after the explosive volcanism happened. So these craters can be used, and the geological inspection of these craters can be used as a laboratory to understand the evolution of events that shaped Mercury's surface. So just to resume what I have just said so far, the surface of Mercury is complementary to that of the Earth, and we found out that its geological history is characterized by a short-lived effusive volcanism phase and a long-lived explosive volcanism phase. Then the hollows are probably the youngest evidence of surface modification we have on Mercury. The tectonics happened mainly in the early formation of the planet, but well correlate to the other, to geochemical terrains, explosive volcanism, and the position of large basins. Its crust, we also saw that its crust is rich in endogenic volatiles that are trapped in the upper layers and cause the formation of hollows. But in the deeper layers, they were also the cause of probably the explosive volcanism. And this is everything from Mercury, and I will be happy to take your questions.